The sun is supposed to be winding down. Solar cycle 25 peaked in late 2024. Every official model said activity would decline from there, and by April of 2026 we should be seeing the quiet drift towards solar minimum. Instead, this morning, a single sunspot fired 2 X-class flares in 7 hours and launched a shockwave at 1,293 kilometers per second toward Earth. The cycle didn't get the memo. Something is happening on the sun right now that the models did not predict, cannot fully explain, and are quietly scrambling to characterize. Stick with me, because by the end of this video you're going to understand why 3 separate active regions are making next week genuinely dangerous. If this already has you thinking, hit like and subscribe to the Skylab, because this story is not going to resolve this weekend. Region 4420 is still rotating towards central meridian. Cycle 25 is still refusing to decline on schedule, and we will be tracking every development as it happens over the coming weeks. You will want to be here for that. Now, let us get into it. Part 1. The event that shouldn't cluster. Something happened on the sun in the last 24 hours that almost never happens. And if you're hearing about it for the first time right now, I need you to understand something before we go any further. The flares themselves are not the story. The flares are the warning signal. The real story is what they're telling us about the condition the sun is in at this exact moment, and what that condition makes possible in the days ahead. Let me walk you through what actually occurred. At 1 minute past 1 in the morning Universal Time, a single sunspot group catalogued as Region 4419 released an X-class solar flare measuring X 2.4 on the intensity scale. That alone would have been the headline event of the week. X-class flares are the most powerful category of solar eruption our classification system accommodates, and in a typical month during solar maximum, you might see a handful of them scattered across different active regions. But this flare did not come alone. Roughly 7 hours later, at 13 minutes past 8 in the morning Universal Time, the same region, the same patch of magnetic chaos on the solar surface, fired off a second X-class flare. This one measured X 2.5, slightly stronger than the first, from the same location, with no meaningful cooldown period between them. 2 X-class flares, 1 region, 7 hours apart. And I want you to sit with how unusual that actually is, because the news coverage has been treating this like just another space weather update, and it is not. Region 4419 is positioned at coordinates designated North 15, West 70. That places it near the western limb of the Sun, meaning it's rotating away from us rather than toward us. The magnetic classification it carries is Beta Gamma Delta, which is the most volatile configuration a sunspot region can hold. You can think of that classification as a kind of structural rating for magnetic instability. Beta means mixed polarities. Gamma means those polarities are tangled in ways that violate clean separation. Delta means opposite polarities are packed so close together they share a single penumbra, which is the grey halo surrounding the dark core of a sunspot. When you see Beta Gamma Delta in the morning forecast, you're looking at a region that has loaded every possible instability into a single magnetic structure. Both flares produced what NOAA classifies as an R3 radio blackout, affecting high-frequency communications across the sunlit side of Earth. That impact was immediate. Pilots flying polar routes, ham radio operators, anyone relying on shortwave bands for communication, they felt this within minutes. The ionosphere responded to the burst of X-ray radiation by becoming dramatically more conductive, which in turn absorbed radio signals that would normally bounce across continents. That was the first punch, and it landed before most of us had finished breakfast. But here's what makes this genuinely unusual. The same region producing repeated high-energy output without stabilization is the kind of behavior that suggests the underlying magnetic structure has not released its stored energy. That should concern us because the standard physics of these events assumes a kind of reset. A region flares, it loses energy, it quiets down while it rebuilds. This region did not quiet down. It fired, paused just long enough to reload, and fired again. And to give you a sense of why this matters even more, let's talk about what was happening before these 2 flares ever occurred. In the roughly 28 hours leading up to the double detonation, Region 4419 produced 6 separate M-class flares. M-class is the tier directly below X-class, still significant, still capable of producing real effects on Earth-facing technology. 6 of them, in just over a day, followed by 2 X-class events. That is not a sudden explosion. That is a progressive, escalating destabilization of a magnetic structure that cannot find a stable configuration. When I say this wasn't a sudden event, I mean it in the most literal physical sense. The region didn't flare twice. It remained unstable across multiple cycles of magnetic reconnection, each one failing to release enough energy to restore equilibrium. That's the key concept I want you to hold in your mind as we go forward. This was a system behavior, not an isolated event. And now here's the question that should be bothering every solar physicist right now. If solar cycle 25 is supposed to be in its declining phase, which is what the official models have been telling us since the beginning of 2025, then why is flare productivity increasing? Why are we seeing the most volatile magnetic configurations of the entire cycle this late in the game? Something is not matching the prediction. And we'll get to that mystery in a later act because it's one of the most interesting anomalies in modern solar physics. For now, focus on the immediate. NOAA's modelling teams have already flagged a partial Earth-directed component embedded in the coronal mass ejection launched by the second flare. A Type 2 radio burst, which is the distinctive signature of a shock wave propagating outward through the solar atmosphere, confirmed that the second flare did not just release electromagnetic radiation. It launched a massive cloud of magnetized plasma into interplanetary space, and some portion of that cloud is now headed in our direction. The flares are over, they ended hours ago, but their consequences are still in transit. What left the sun this morning hasn't reached us yet. The electromagnetic radiation arrived at the speed of light, which is why the radio blackouts were instantaneous. But the physical matter, the plasma, the magnetic field structures, those travel slower, they take time, and while they travel, every single condition on the Earth-facing side of space is currently quiet, waiting in a state of deceptive calm that will end sometime this weekend. The real event is not the flare, it's what the flare launched, and what it launched is coming. Part 2. The physics of no cooldown. To understand why region 4419 behaved the way it did, we need to talk about magnetic reconnection, because that is the mechanism that drives every solar flare, every coronal mass ejection, and every major space weather event that has ever threatened our technological civilization. Magnetic reconnection is what happens when oppositely directed magnetic field lines get pushed together until they break and rejoin in a new configuration. When that rejoining happens, the magnetic energy that was stored in the twisted, tangled structure gets converted almost instantaneously into heat, light, and kinetic motion. A solar flare is the observable signature of that energy conversion. The X-rays, the ultraviolet light, the visible brightening, all of it is the sun essentially short-circuiting a stressed magnetic structure and dumping the excess energy into space. Under normal conditions, here's what should happen after a large flare. The region should release its stored energy, the magnetic structure should relax toward a lower energy configuration, and the area should enter a kind of recovery period during which it rebuilds stress slowly before possibly flaring again. That recovery can take hours or days depending on the region's size and complexity. What it should not do is immediately reload and fire again at the same energy level within 7 hours of the first event. Region 4419 did exactly that. And the most coherent explanation for how that's even possible is that this region contained multiple independent energy reservoirs. You can think of it like a building with several separate electrical systems. Blowing out one circuit doesn't affect the others. Each of them can fail independently. Each of them can fail catastrophically. And each of them can fail in rapid succession if the underlying conditions that caused the first failure are still present in the other systems. The beta-gamma-delta classification is critical to understanding why this is even possible. In a simple active region, you have one positive polarity area and one negative polarity area. Separated by a clean dividing line called the polarity inversion line, the magnetic structure is tidy, predictable, one failure mode. But in a beta-gamma-delta region, you have multiple polarity inversion lines, sometimes tangled, sometimes braided together, each one representing an independent failure point. Imagine a building with not one load-bearing wall but dozens, each of them under different stresses, each of them capable of cracking at a different moment. This is what region 4419 appears to have been. Not a single stress structure, but a distributed network of stress structures. and what we witnessed this morning may not have been a region flaring twice. It may have been a region undergoing distributed magnetic collapse, with different failure points triggering in sequence as the overall stability of the whole system degraded. Solar physicists have a concept called magnetic helicity, which is essentially a measure of how twisted and braided the magnetic field lines are within a region. Helicity builds up over time as the region rotates and as different magnetic flux elements emerge from below the solar surface and interact with what's already there. High helicity means lots of stored energy, and when helicity reaches certain critical thresholds, the region becomes prone to cascading failures, where one reconnection event creates conditions that make further reconnection events more likely. The swarm of M-class flares we saw in the 28 hours before the double X-class detonation can be interpreted in this framing as precursor events, smaller stress releases. The system trying to find equilibrium and failing. Each M-class flare may have redistributed magnetic stress rather than actually releasing it, loading different parts of the region toward their own failure thresholds, and when the first X-class finally broke, it didn't resolve the underlying problem, it just exposed how much more energy was still waiting in other parts of the structure. There's an under-discussed concept in solar physics that's relevant here: flare clustering, meaning multiple flares from the same region in rapid succession, can be a signature of an approaching critical instability threshold. It's the kind of behavior you sometimes see right before a region produces its largest event. The implication is uncomfortable. Region 4419 may not have peaked yet. It may have been approaching a cascade failure state, and what we observed was either a partial release or a prelude to something larger that might still be on its way, depending on how much of the region's magnetic energy has now actually been dissipated. I want to be careful here and acknowledge the limits of what we actually know. Direct imaging of magnetic topology at the resolution required to confirm any of this is not available in real time. We're inferring structure from indirect measurements, comparing signatures to previous events, running models that have their own assumptions baked in. What I'm describing is consistent with the data, but it is not the only possible interpretation. Other solar physicists will look at the same data and emphasize different aspects. That's normal. Space weather science is a field where genuine uncertainty is the default state. But even setting aside the deepest questions about Region 4419's internal structure, what matters more for our immediate situation is not what happened on the Sun. It's what's moving through space right now as a direct consequence of what happened on the Sun. Because the flare itself is done, the energy release is over, but the plasma that got launched into interplanetary space during that second X-class event is still out there, still moving, still heading, at least partially, in our direction, and the speed and structure of that cloud and what it encounters along the way is what will actually determine whether this becomes a minor inconvenience or something more serious. What matters now is not what happened on the Sun, is what's moving through space, and that is a separate story with its own physics and its own unpredictability. Part 3. The CME that might not stay independent. The coronal mass ejection launched by the X-2.5 flare is moving through interplanetary space at an estimated shock speed of 1,293 km per second. That number comes from the Type 2 radio burst signature, which allows us to track shock front propagation through the solar corona and into the solar wind. To put that velocity in context, the median speed for coronal mass ejections is around 400 km per second. The solar wind itself typically moves at between 300 and 500 km per second in quiet conditions. This particular CME is moving at more than 3 times the median speed. It is not just a fast ejection, it is a shock-driven event, meaning it's travelling faster than the ambient solar wind and is therefore ploughing a pressure wave through the medium in front of it, much like a supersonic aircraft pushes a shock cone through the atmosphere. The distinction between shock-driven CMEs and slow CMEs matters enormously for what happens when they reach Earth. A slow CME drifts toward the planet and gradually merges with the existing solar wind structure, often producing only modest geomagnetic effects. A shock-driven CME arrives with an abrupt pressure front that slams into Earth's magnetosphere, compressing it on the sunward side and potentially triggering a cascade of effects in the magnetotail on the night side. The initial impact alone, before any prolonged magnetic coupling, can produce measurable voltage fluctuations in long conductor systems on the ground. But here's where the situation gets genuinely interesting, and where we need to start thinking about interactions rather than individual events. there was an earlier coronal mass ejection associated with an M-class flare on April 23rd that is also currently in transit. That earlier CME is slower than the shock-driven event we're now tracking, which means, depending on exact trajectories and arrival geometries, we have a real possibility that the faster CME will catch up to and interact with the slower one somewhere in the space between the Sun and Earth. This kind of event has a name. Space weather physicists call it CME cannibalization. When a fast CME overtakes a slower one, they don't simply pass through each other, they merge. The faster structure compresses into the slower one, the magnetic fields of both events combine and restructure, and the resulting merged cloud can have dramatically different properties than either CME would have had on its own. Densities can increase, magnetic field strengths can amplify, velocity gradients can steepen, and most importantly for our purposes, the orientation of the magnetic field within the merged structure becomes highly volatile and difficult to predict. That orientation, specifically the north-south component of the magnetic field known as BZ, is arguably the single most important parameter for determining how severe a geomagnetic storm becomes when a CME arrives at Earth. If BZ is pointing northward, meaning aligned with Earth's magnetic field at the point of impact, the CME essentially bounces off the magnetosphere with minimal coupling. Minor effects, possibly beautiful auroras at high latitudes, not much else. But if BZ is pointing southward, meaning anti-parallel to Earth's field, the incoming magnetic structure couples directly with our magnetosphere through a process called reconnection, injecting enormous amounts of energy into our magnetic environment, driving geomagnetic storms that can reach levels dangerous to satellites, power grids, and communication systems. The problem with CME cannibalization is that it scrambles BZ in ways we cannot predict until the merged cloud arrives. Two CMEs might each have had benign BZ orientations individually. Merged, they might produce a highly volatile BZ profile that flips between orientations, and if any portion of that profile is strongly southward when it interacts with Earth, the geomagnetic response can be far worse than forecasters expected based on either CME alone. There is a precedent for this kind of escalation that solar physicists talk about frequently. In May of 2024, a sequence of CMEs interacted in transit and produced what became known as the Gannon storm, which reached G5 extreme levels on the NOAA scale, the highest possible classification. The initial forecast had not anticipated an extreme event. The escalation happened during transit through exactly the kind of interaction physics I'm describing. That event produced auroras visible across much of the continental United States, caused measurable impacts to satellite operations, and demonstrated in unmistakable terms that initial flare magnitude does not determine final storm strength. I want to emphasize that point because it runs counter to how most media coverage of space weather works. A large flare happens, and the coverage treats the flare's size as if it's a reliable predictor of what will follow. It is not. The structure of the CME in transit, the interactions it undergoes, the magnetic configuration it happens to have when it reaches Earth, those factors can easily dwarf the influence of the original flare energy. A moderate flare that produces a well-configured CME can cause more geomagnetic disturbance than an extreme flare whose ejected material happens to have a north-pointing magnetic field when it arrives. Our models have real limitations here. NOAA's SPACE, Weather Prediction Center, uses ensemble modeling, which means running the same CME event through dozens of simulations with slightly different initial conditions and assumptions to produce a range of possible arrival times and intensities. The spread in those ensemble results tells us something important. For this current event, the spread is wide. The uncertainty is real. The first shock speed estimate was actually 1,869 km per second, before being revised down to 1,293. That kind of revision is normal. It reflects the difficulty of measuring these parameters in real time from imperfect data. Space weather risk is fundamentally nonlinear. Small differences in input conditions can produce large differences in outcomes, and we often don't know which inputs mattered most until after the event is over. That's the reality forecasters are working with, and the central concern right now is not what we've already observed. It's what we might still observe in the next 72 hours as these structures interact and arrive. The sun didn't just fire once. It's in a state where it can fire again. That is the warning signal we need to keep in mind as we move through the rest of this analysis. Part 4, the signal hidden in the radio noise. One of the most informative aspects of the Dual X-class event, and one of the aspects that's getting the least attention in public coverage, is the radio emission profile associated with both flares. When we look at the radio burst signatures, we're not just seeing confirmation that flares happened, we're seeing detailed information about what kind of particle acceleration occurred, and that information tells us a great deal about what's now travelling toward Earth. Two types of radio bursts are particularly significant here. Type 2 bursts are the signature of shock waves propagating outward through the solar atmosphere. They appear as slowly drifting emission features on radio spectrograms, drifting because as the shock moves outward into less dense plasma, the frequency of radio emission it produces decreases. Type 2 bursts confirm that a CME with a shock front has been launched, and they allow us to estimate shock speed directly from the frequency drift rate. Type 4 bursts are different. They indicate populations of energetic electrons that have been trapped within moving magnetic structures, continuing to emit radio waves as they gyrate around the field lines inside a propagating plasma cloud. When you see both Type 2 and Type 4 signatures together, you're looking at an event that combines a shock wave with substantial populations of trapped energetic particles. And that combination is what produces some of the most consequential space weather outcomes. The 10-centimetre radio burst associated with the X2.5 flare reached 570 solar flux units at peak, against a background level of 128 solar flux units. That is roughly 4.5 times normal background emission, and it's a significant anomaly. 10-centimetre radio emission correlates with electron density and acceleration efficiency in the flaring region. Stronger emission means more electrons were accelerated to high energies. More high-energy electrons means more potential for downstream effects, including satellite charging, communication disruption, and radiation exposure for anyone outside Earth's protective atmosphere. What we can infer from these radio signatures, taken together, is that this event was unusually efficient at producing energetic particles, not just photons, not just electromagnetic radiation that stopped being relevant once it passed us at the speed of light, but protons and electrons accelerated to energies where they can physically damage spacecraft electronics, degrade solar panels, and pose risks to astronauts on the International Space Station and anyone in polar flight paths. NOAA currently assesses a 25% probability of an S1 minor radiation storm over the next 24 hours, driven by the particle population accelerated during this event. That probability is not negligible, and it's separate from the geomagnetic storm risk that comes later when the CME arrives. The radiation storm is driven by particles that travel much faster than the CME, reaching Earth within hours rather than days. Before the flares occurred, we also saw an elevated flux of 2 million electron-volt electrons in the magnetosphere, reaching high levels that can cause internal charging effects in geostationary satellites. Internal charging is one of those underappreciated space weather hazards. It occurs when high-energy electrons penetrate spacecraft surfaces and deposit charge inside sensitive electronics, where grounding and shielding can't easily drain it away. When enough charge accumulates, you get electrostatic discharge events that can damage components, corrupt data, or in extreme cases disable entire systems. Satellite operators track this flux continuously and take defensive actions when it spikes, but those actions have limits. The radio emissions matter in another way that often goes unmentioned. Strong radio bursts at these frequencies can directly interfere with radar systems, GPS signals, and high-frequency communications even beyond the ionospheric absorption effects. Imagine a dish antenna trying to track a satellite while the sun itself, suddenly, becomes a radio source 100 times brighter than the signal you're trying to receive. That kind of interference is hard to filter around. Military radar systems, air traffic control, maritime communications, they all have to cope with this when major flares occur. We've already observed the R3 radio blackout from this event. That happened in real time. It was the first impact phase, arriving at the speed of light with the X-ray radiation from the flares themselves. That phase is over. The ionosphere is recovering. High-frequency communications are returning to normal. But the second phase hasn't started yet. The geomagnetic response, the part driven by the arrival of the CME itself, is still in the future. It hasn't begun. And the timing matters because it means we're currently in a temporary calm, with the full consequences of this event still in transit. That calm is deceptive, Because right now, if you checked your weather app for space weather conditions, you might conclude everything was fine, and technically at this moment it is, but the conditions we're in right now are not a stable state, they are a waiting state. Part 5. The quiet before arrival. At the time I'm recording this, solar wind conditions near Earth are remarkably uneventful. The wind speed is hovering around 383 km per second and actually decreasing slightly. The total magnetic field strength, which we call BT, is sitting near 4 nanoteslas, which is low. The north-south component, BZ, is fluctuating weakly around zero with no sustained orientation in either direction. The planetary K-index, which is the most commonly cited measure of overall geomagnetic disturbance, is reading around 1.3. That's quiet. Almost boring. There is currently no geomagnetic stress on Earth's magnetosphere. None. And that is exactly the point. The sun has already fired. The consequences are already in transit. But the moment you're listening to this, if you're listening as it happens, Earth is sitting in a period of unusual calm, while roughly 93 million miles of space still separates us from the plasma cloud that's coming. This calm has a name in space weather physics. It's called the preconditioning state. And how the magnetosphere is preconditioned before a CME arrival actually influences how it responds to that arrival. That's one of those details that doesn't often make it into mainstream coverage, but it's physically significant. Think about it this way. Earth's magnetosphere is a dynamic system, with its own internal currents, its own trapped particle populations, its own pressure distributions. When a CME slams into it, the response depends not just on the CME's properties, but on what state the magnetosphere was already in when impact occurred. A pre-stressed magnetosphere, one that has been dealing with elevated solar wind activity for days, can sometimes absorb additional impact with less dramatic response. A relaxed, low-activity magnetosphere, like the one we have right now, can respond more acutely to a sudden pressure increase. The math of this is complicated, and the outcomes are not easily predictable, but the general principle is established. There are 2 scenarios worth considering. In the first scenario, the current calm state of the magnetosphere acts as a kind of shock absorber. The CME arrives, the sunward side of the magnetosphere compresses, some energy is dissipated through various internal processes, and the overall geomagnetic response stays within the forecast range of G1 to G2. In the second scenario, the same calm state actually makes things worse by allowing the incoming shock to compress the magnetosphere more dramatically than it otherwise could, producing a larger initial disturbance and potentially setting up conditions for a more intense storm response. Which scenario plays out depends on factors we can't fully predict until the CME arrives and we measure its properties directly. This is one of the fundamental constraints of space weather forecasting. We're making predictions about a system whose critical parameters can't be fully characterized until the event is actually happening. Complicating the picture further, we have a high-speed solar wind stream currently flowing from a coronal hole on the Sun. Coronal holes are regions where the Sun's magnetic field opens out into space rather than forming closed loops, and they allow the solar wind to escape at higher velocities than from other regions. The stream from this particular coronal hole is expected to reach Earth around the same general window as the CME we've been discussing, maybe overlapping, maybe sequential. The timing isn't precisely nailed down, and small differences in arrival sequence can produce very different outcomes. When a CME arrives in a background of already elevated high-speed solar wind, the interaction can be particularly disruptive. The trailing edge of the CME gets compressed against the faster-moving stream behind it, intensifying density and magnetic field structures in that region. Geomagnetic disturbance that might otherwise subside within 12 hours can extend to 36 hours or longer as the magnetosphere continues to process one perturbation after another. Multiple moderate inputs can produce a geomagnetic response that's greater than the sum of its parts. The SWPC timing estimates put expected arrival somewhere in the late hours of April 25th into April 26th. Forecasters are calling for G1- storm conditions with a realistic possibility of G2 moderate storm conditions, but these are baseline forecasts. They assume relatively benign CME properties and no major interaction effects. If the CME merger scenario plays out, if BZ comes in strongly southward, if the coronal hole stream amplifies the response, we could see higher storm levels. Conversely, If everything arrives with favourable geometry, the storm could underperform the baseline forecast. That range of possibility is not because forecasters are being evasive, it's because the underlying physics genuinely contains that much uncertainty. Space weather is a forecasting problem in the same category as hurricane intensity prediction. You can narrow the cone, but you cannot eliminate it. Energy is already on the way. The decisions about how that energy will affect us are not being made by forecasters. They're being made by physics we cannot fully observe until it's already underway. But here's the thing that tightens the whole picture. The sun isn't done producing energy. What we've been discussing up to this point, the event that already happened, is not actually the most important part of this story. The most important part is what's still on the solar disk right now, facing us, loaded and active. Because while the CME from the X2.5 flare is still in transit, there are 3 different active regions on the sun's face capable of producing new eruptions, some of them in geometries far more threatening to Earth than region 4419. What's on the solar disk right now matters more than what already happened, and that's where we need to look next. Part 6. 3 delta regions, 1 disk. The central thread of everything I've been telling you, the argument I want you to hold on to, is that the dual X flare from region 4419 is not the danger. It's the evidence of what the current configuration of the sun is capable of producing. And to understand why that evidence matters, you have to look at what else is currently loaded on the solar disk, because region 4419 is not alone. At this moment, there are 3 distinct active regions on the Earth-facing side of the sun carrying beta-delta or beta-gamma-delta magnetic classifications. Region 4419, which we've already discussed at length, sitting near the western limb. Region 4420, which is currently rotating toward the central meridian, and region 4423, a newly emerged region that's already producing M-class activity, despite being barely old enough to have fully formed a stable sunspot structure. 3 delta regions, on 1 solar disk, at the same time. The delta classification matters more than any other parameter when it comes to predicting X-class flare productivity. Statistical studies of major solar flares over multiple solar cycles have repeatedly shown that delta-type sunspot regions are responsible for the overwhelming majority of the most energetic events. A region without delta structure can still produce flares, but the probability distribution shifts dramatically towards smaller events. Add delta structure into the mix and you unlock the upper end of the flare energy spectrum. Having 1 active delta region on the disk at any given time is not unusual during an active phase of the solar cycle. Having 2 is noteworthy. Having 3 simultaneously is genuinely rare, and it's the kind of configuration that space weather forecasters flag internally as elevated baseline risk. Not because any one of those regions is necessarily about to produce an X-class flare in the next hour, but because the probability of at least one of them doing so somewhere in the coming days is meaningfully higher than normal. This multi-region activity is telling us something about the sun that goes beyond the behaviour of any individual sunspot group. The solar surface is not just hosting one local instability right now, it's displaying a pattern of global magnetic instability distributed across multiple regions. Whatever physical process is loading energy into these regions is doing so coherently, across significant portions of the disk, rather than in the isolated way we'd expect during a quieter phase of the cycle. This is the configuration that produced the dual X flare, and there's no physical reason to assume that the same configuration cannot produce similar events from the other regions, especially if one of them reaches the same critical instability threshold that region 4419 apparently reached. The risk window here is not the next few hours, it's the next 1 to 2 weeks. During that window, any of these 3 regions could transition from producing M-class flares to producing X-class flares, and the geometry of each region's position on the disk will determine how directly any resulting CME would impact Earth. What region 4419 demonstrated this morning was not just a local event, it was proof of concept. Proof that the current solar configuration is capable of producing dual X-class flares from a single region in rapid succession, and proof that similar events can happen from the other regions that share this configuration. That's the central thread I want you to keep holding on to as we look at what the other regions might do, because the one we should be watching most carefully is not the one that already fired. Part 7. Region 4420, the one that matters. Region 4420 is currently the largest active region on the Sun. It covers an area of approximately 250 millionths of the solar hemisphere, which is a standard way of measuring sunspot group size. That's substantially larger than region 4419 was when it produced today's X-class flares. Region 4420 contains approximately 20 individual sunspots distributed across a complex magnetic structure, with shear developing between polarity regions in ways that have been increasing over the past several days. This region is on the move. Specifically, it's rotating toward the central meridian of the Sun, which is the imaginary line running north-south directly across the Sun's face from Earth's viewpoint. When an active region is near the central meridian, any CME it produces is maximally Earth-directed. The geometry isn't glancing, it isn't tangential. The ejector travels approximately along the Sun-Earth line, and the magnetic cloud arrives with Earth squarely in the middle of its propagation path. Currently, region 4420 is assessed as having a lower X-class flare probability than region 4419 was before today's events, but that probability assessment is a snapshot, and the relevant trend is that region 4420's magnetic complexity is increasing. More sunspots are emerging. The shear between polarity regions is intensifying. The delta structure is strengthening. All of these are signs that the region is in a build-up phase rather than a stable or decaying phase. Complexity growth in active regions typically precedes flare escalation. Not always. Some regions grow in complexity and then gradually stabilize without producing major flares, but the correlation between rising complexity and subsequent X-class events is strong enough that when forecasters see a region moving in this direction, they adjust their probability estimates upward as the growth continues. If region 4420 follows the trajectory that region 4419 followed over the past week, here's what that would look like. Several days of M-class activity gradually increasing in frequency, continued build-up of magnetic complexity, one or more precursor events that redistribute stress without fully releasing it, then a major X-class event, potentially followed by additional large flares if the region has multiple energy reservoirs in the way region 4419 apparently did. The critical difference is geometry. Region 4419 produced its X-class flares while positioned at West 70, meaning it was well past the central meridian and rotating toward the far side of the Sun. Any CMEs from that position are launched at a significant angle away from the Earth-Sun line. The Earth-directed component of today's CME exists, but it's partial because the primary direction of the ejector is generally westward of Earth. If region 4420 produces a similar event in the coming days, it will likely do so while positioned much closer to the central meridian. Fully Earth-facing, no glancing geometry, no partial component. The entire propagation path of the resulting CME would intersect Earth's location almost directly, and the implications of that geometry for geomagnetic storm intensity are substantial. This is why region 4420 matters more than the region that already fired. The region that already fired has already done its thing, and we're now watching the downstream consequences play out. Region 4420 hasn't fired yet. And if it does with anything approaching the energy release we saw from region 4419, the geometry will turn what was a partial Earth-directed event into a full Earth-directed event. Region 4419 was the test case. Region 4420 is the potential repeat performance, with the stage lights pointed directly at us instead of off to the side. Part 8. Region 4423, the sleeper variable. While attention is rightfully focused on region 4419's aftermath and region 4420's approach towards central meridian, there's a third region on the disk that deserves attention, and it's the one that's hardest to predict. Region 4423 is a newly formed active region. It has been growing rapidly over the past several days, expanding from essentially nothing to a recognizable sunspot group with beta-delta magnetic structure. It has already produced an M-class flare during its brief lifetime, which is faster than most emerging regions develop flare productivity. That's notable. Regions typically take a week or more to mature into significant flare producers. Region 4423 got there in days. The fact that it's already delta-classed at such a young age means the magnetic structure emerging from below the solar surface has been loaded with the kind of complexity that produces major flares from the start. It didn't have to grow into delta structure, it came up delta. That suggests the energy source feeding this region is not incidental, it's substantial, and the region has the capacity to continue developing in ways that could make it a serious flare producer over the next week or two. Emerging regions present a particular forecasting challenge because they haven't established a track record. We don't have a baseline for how they typically behave, how they build stress, what flare rates they'll produce. All of those assessments require historical observation of the specific region in question. For Region 4.423, there's very little history yet. Everything we're predicting is based on analogies to other emerging delta regions from past observations. There's a hypothesis worth considering, though it remains speculative and hasn't been proven. Multiple active regions on the same solar disk may not evolve independently. Large-scale magnetic connectivity in the corona can link regions together in ways that allow stress in one region to influence stress in another. If Region 4.423 is magnetically connected to Region 4.420, or even to the remnants of Region 4.419, then events in one region could trigger or contribute to instabilities in the others. This idea of the solar surface as an interconnected system, rather than a collection of isolated active regions, is gaining traction in some research circles. It would explain phenomena like sympathetic flaring, where multiple regions flare in close succession despite being physically separated on the solar disk. If the hypothesis is correct, then having 3 delta regions active simultaneously isn't just a statistical coincidence. It's a configuration that may actually increase the probability of coupled behavior, where one region's destabilization propagates to others through large-scale field connections. The uncertainty around Region 4.423 cuts both ways. On one hand, it might continue to produce M-class flares and gradually mature into a routine active region without ever reaching the threshold for an X-class event. That would be the unremarkable outcome. On the other hand, its rapid development and existing delta structure mean it could escalate much faster than we expect, producing a major event with very little warning time. The risk here is specifically the risk of surprise. An X-class flare from Region 4.423 in the next week would be harder to anticipate than one from the other 2 regions, because its behavior is still establishing itself. And in space weather, surprise events tend to be the ones that catch infrastructure operators unprepared. Everything about the current solar situation, the multi-region activity, the delta configurations, the rapid development of new regions, supports the argument that the dual X flare from Region 4.419 was not an endpoint. It was the beginning of a risk window. The Sun has demonstrated what it can do in this current configuration, and the other active regions are continuing to build the kind of complexity that made that demonstration possible. The next major flare could come from a region we've been watching carefully, like 4.420, or it could come from a region we're still trying to characterize, like 4.423. The unpredictability itself is part of the risk profile. Part 9. Rotation is the real clock. Something worth explaining because it governs the entire threat window we're currently in, is that the Sun rotates. It takes about 27 days to complete a single rotation as seen from Earth. And that rotation means every active region on the solar disk is continuously moving across our field of view, from east limb to west limb over the course of roughly 2 weeks. This matters because an active region's geo-effectiveness, meaning its potential to produce space weather impacts on Earth, depends enormously on where it is in its rotation across the disk. A region near the east limb has just rotated into view and is facing generally away from Earth. Any flare or CME it produces will launch ejecta largely to the east of the Earth-Sun line. A region near the west limb is about to rotate out of view, like Region 4.419 was this morning, and its ejecta launches largely to the west of the Earth-Sun line. Only regions near the central meridian produce ejecta with paths that closely align with the Sun-Earth line, meaning their impacts on Earth are maximized. The geo-effective window for any given region is typically a few days on either side of central meridian transit. Outside that window, even a powerful flare tends to produce only glancing space weather impacts, if any at all. Inside that window, even a modest event can produce significant geomagnetic effects because all of its launched material is aimed directly at us. Here's how the clock is currently running. Region 4.419, the one that already fired, is past central meridian and heading toward the west limb. Its future flares, if any occur, will become progressively less geo-effective as it rotates further west. Within a few days, it will rotate out of view entirely, and any continued activity from it will no longer directly threaten Earth. Region 4, 420 is currently approaching central meridian. Over the next 4 to 11 days, it will transit through the peak geo-effective zone. Any major flare it produces during that window would be launching ejecta directly toward Earth. After that window, it too will rotate past central meridian and begin heading toward the west limb. Region 4423 is still in a growth phase, and its position will depend on exactly when it fully forms and whether it continues to develop. But if it maintains its current trajectory, it will also transit through the geo-effective zone sometime in the next 1 to 2 weeks, giving us another period during which its ejecta could be directly Earth-aimed. The risk isn't evolving linearly, it's evolving with the rotation. Today's threat from region 4419 is relatively contained because of the region's limb position. The next several days will bring the largest region, region 4420, into the zone where its potential impact on Earth would be maximised. The week after that, region 4423 may be in a similar position depending on its development. When I say the real danger is not the flare that already happened, but the flares rotating into direct alignment with Earth, this is what I mean. The solar rotation is the clock, and we're in the early stages of a threat window that will remain elevated until these regions either produce their events or rotate past the geo-effective zone without doing so. Part 10. The Weekend Impact, Baseline Reality. Let me set expectations carefully for what we should actually expect from the immediate event, because realistic expectations are the best defense against both complacency and hysteria. NOAA's Space Weather Prediction Center has forecast G1 minor storm conditions as the baseline expectation for the CME arrival late on April 25th through April 26th, with a realistic possibility of G2 moderate storm conditions if interaction effects amplify the response. That forecast, as it stands, describes a reasonably manageable event by space weather standards. What does G1 to G2 actually look like in practice? Aurora expansion toward lower latitudes than usual, potentially making the northern lights visible in parts of the northern United States, northern Europe, and similar latitudes that don't normally see auroras. Minor fluctuations in power grid voltage at high latitudes, well within the operational margins of modern grid infrastructure. Minor disruptions to GPS accuracy, primarily affecting surveying-grade applications that rely on precision positioning rather than consumer navigation. Some degradation of high-frequency radio communications at high latitudes. Some increased satellite drag in low Earth orbit, with small orbital adjustments potentially required but no immediate operational concerns. This is not catastrophic. This is the kind of space weather event that occurs multiple times per year during an active solar cycle, and most people go about their daily lives without ever noticing it happened. If you're an aurora enthusiast, it's an exciting opportunity. If you operate satellite constellations in low Earth orbit, it's an operational nuisance. If you're a grid operator at high latitudes, it's something you log and monitor but don't typically respond to aggressively. The average person experiences no detectable impact. I want to be clear about that, because the tone of this analysis has been appropriately serious, and I don't want anyone coming away thinking that the weekend is going to bring some dramatic collapse of modern civilization. It isn't. The baseline forecast describes an event that our infrastructure is designed to handle. But here's the thing about baseline forecasts. They're baselines. They assume the physics plays out as expected, with no major surprises in the CME's properties or its interaction with the solar wind environment. And the current event has more than one amplifier that could push it above the baseline. The first amplifier is the potential CME interaction we discussed earlier. If the X2.5 flare's CME overtakes and merges with the earlier M-class CME, the resulting combined cloud could have substantially different properties than either event alone: higher density, stronger magnetic field, potentially more volatile BZ orientation. A G1 baseline could become G2, or G2 could become G3, depending on how that merger plays out. The second amplifier is the coronal hole high-speed stream. If that stream arrives in the same window as the CME and contributes to compressing or sustaining disturbance, the duration and intensity of the geomagnetic response can both increase. A 6-hour G2 event could become an 18-hour G2 event, or it could briefly touch G3 levels during peak compression. The baseline forecast is the floor, not the ceiling. Real outcomes depend on interaction dynamics that cannot be fully predicted until they're underway. That's not a hedge. That's the actual structure of space weather forecasting. What we know right now is that this weekend will include a geomagnetic storm. What we don't know yet is whether it will be a minor storm we barely notice, a moderate storm with some practical impacts, or something larger if multiple amplifying factors align. The central thread here is still the same. The sun fired a warning shot. The consequences of that shot are arriving, and the conditions that made the shot possible are still present, still capable of producing additional events, still potentially ready to compound whatever the weekend brings. This is the opening move, not the main event. Part 11. When CMS interact. The physics of CME-CME interaction is one of the most active areas of space weather research, and it's also one of the hardest to model accurately, precisely because the interactions themselves happen in regions of space where we have very limited direct observational coverage. When two CMEs encounter each other in interplanetary space, several things happen simultaneously. The magnetic clouds within each CME begin to interact and restructure, with field lines from one cloud potentially reconnecting with field lines from the other. The shock fronts, if both CMIs had them, can merge into a single stronger shock, or can produce complex multi-shock structures with intervening plasma regions. The plasma densities compress at the interaction boundary, producing higher than ambient density regions that can significantly affect how the combined structure transfers energy into Earth's magnetosphere on arrival. Perhaps most importantly for practical impact prediction, the BZ orientation within the merged structure can become dramatically more variable than it would have been in either CME individually. A CME that would have arrived with a relatively stable northward or southward BZ can, after interaction, arrive with a BZ profile that flips orientation multiple times over the course of the event. Each flip can trigger a new round of energy coupling with Earth's magnetosphere, and a sequence of southward-pointing BZ episodes can drive cumulative geomagnetic disturbance that exceeds what either source event would have produced alone. The forecasting problem here is genuinely difficult. We have coronagraph observations that let us watch CMEs leave the Sun. We have some spacecraft in the solar wind at the Lagrange 1 point, roughly 1 million miles upstream of Earth, that can measure properties of the CME when it arrives there, giving us about 30 minutes to an hour of warning before Earth impact. But the volume of space between the Sun and the Lagrange 1 point is largely unobserved. We can model what happens during transit. We cannot directly watch it happen in real time, not with the precision we'd need to resolve interaction details. This means the most dangerous potential effects of CME interaction emerge during a phase that we cannot observe until it's effectively over. By the time we measure a merged cloud at Lagrange 1, the interaction has already happened. The BZ profile we measure is the BZ profile we're going to experience. We can warn grid operators and satellite operators about what's incoming, but we can't change the nature of what's arriving. The contrast with isolated CMEs is stark. A single CME, well characterized by its coronagraph signature and transit models, can produce a forecast with relatively narrow uncertainty bounds. Arrival time accurate to within a few hours. Intensity predictable within a factor of 2. BZ orientation estimable from the magnetic structure of the source region, though never perfectly. With interacting CMEs, all of those predictions become noisier. Arrival time becomes broader. Intensity can swing by factors larger than 2. BZ orientation becomes genuinely hard to estimate in advance. For the current event, the question of whether the X2.5 CME will actually catch and merge with the earlier M-class CME remains unresolved. Some ensemble model runs produce mergers, others produce sequential arrivals without significant interaction. The truth will become clear as both structures approach Lagrange 1 and we get direct measurements. The central thread is still the same. The Sun produced a major event, and the consequences of that event are evolving as they travel through space. What started as a relatively predictable forecast, one event, one trajectory, one set of expected effects, has become a more complicated forecast involving potentially multiple interacting structures with amplifying physics, and we can't fully resolve the uncertainty until impact is imminent. Another factor may already be amplifying the situation in ways that will only become visible when they interact with everything else that's arriving. That's where coronal hole streams come in. Part 12. The hidden amplifier, coronal hole stream. Earlier, I mentioned the high-speed solar wind stream currently flowing from a coronal hole on the Sun. I want to return to that topic briefly, because it's one of those factors that often goes unmentioned in mainstream space weather coverage, but it can significantly alter how a given CME event affects Earth. Coronal holes are regions on the Sun where the magnetic field is configured in an open topology rather than a closed one. In closed field regions, magnetic loops rise from the solar surface and return to it, trapping plasma. In open field regions, the field lines extend outward into interplanetary space without returning, which allows plasma to escape more readily along those field lines. The solar wind from coronal holes is faster, hotter, and lower in density than the slow solar wind from closed field regions. When a high-speed stream from a coronal hole arrives at Earth in isolation, it typically produces modest geomagnetic effects, often reaching G1 or occasionally G2 levels. It's a relatively common source of minor storms, and it's one of the primary drivers of recurrent geomagnetic activity. Because coronal holes can persist for multiple solar rotations, producing similar stream events every 27 days. When a high-speed stream arrives at Earth roughly simultaneously with a CME, the interaction dynamics can amplify the overall response. Specifically, when a CME is followed closely by a high-speed stream, the stream can compress the trailing edge of the CME against the slower solar wind ahead, intensifying density and magnetic field structures in that region. Geomagnetic disturbances that would otherwise decay over 12 to 24 hours can extend to 36 hours or longer as the magnetosphere continues to respond to the compressed trailing structure. For the current event, the timing of the coronal hole stream arrival is expected to overlap with the tail end of the CME impact window. That overlap is what matters. If the stream arrives during peak CME response, we could see extended storm durations. If it arrives after the CME has mostly passed, it may produce a secondary disturbance without significantly amplifying the main event. The exact timing matters in ways that our models can only approximately capture. The broader principle here is that space weather events don't happen in isolation. The current solar wind environment is influenced by everything happening on the Sun simultaneously, and multiple moderate inputs arriving in sequence or overlap can produce outcomes that are nonlinear in their combined effect. A standalone G1 event might become a G2 extended event under the right amplifying conditions. A standalone G2 event might become a brief G3 with similar amplification. What region 4419 demonstrated, and what the broader solar configuration is suggesting, is that the current solar environment is producing repeated moderate to strong inputs into near-Earth space. Each input on its own might be manageable. But cumulative exposure to multiple inputs in close succession can stress systems that are designed around the assumption of isolated events. Even a moderate event can escalate when it combines with the current unstable solar configuration. That's the connection back to the central thread. The danger isn't any one event, it's the accumulation of events and the interactions among them in an environment that's producing more of them than the baseline forecasts anticipated. Part 13. The failure mode. Nobody models well. Of all the parameters that determine how severe a geomagnetic storm becomes, the one that matters most is also the one we predict worst. It is called BZ, and if you have never heard of it before, that is not an accident. It does not make it into most news coverage because it is invisible, it is counterintuitive, and it refuses to cooperate with the clean narratives that mainstream space weather reporting tries to build. But it is the single hidden variable that determines whether this weekend's storm is a minor inconvenience or something considerably worse, and understanding what it is and why we cannot predict it is essential to understanding why forecasters are being so carefully non-committal about the coming days. BZ is the north-south orientation of the magnetic field carried by the solar wind or by a coronal mass ejection as it arrives at Earth. Every cloud of solar plasma carries its own magnetic field, threaded through it, frozen into it by the physics of how ionized gas interacts with magnetic structures. That field has three components, one pointing along the Sun-Earth line, one pointing east-west, and the one we care about, the one pointing north or south. That third component is BZ. Earth's own magnetic field has a northward orientation in the region, where the solar wind encounters it on the sunward side. This is the geometry that has protected our planet from solar radiation for billions of years, deflecting charged particles around the magnetosphere rather than letting them stream into the atmosphere. When the incoming BZ is also northward, the two fields are parallel. They do not couple efficiently. The solar wind slides around the magnetosphere like water flowing past a stone, and almost none of its energy gets transferred into our magnetic environment. Geomagnetic activity stays low, regardless of how fast the solar wind is moving, regardless of how dense it is, regardless of how impressive the source flare looked on solar imagery. A 10 million mile/hour CME with northward BZ will produce a shrug. Aurora enthusiasts go home disappointed. Grid operators go back to their coffee. When the incoming BZ is southward, everything changes. The two fields are now anti-parallel, pointing in opposite directions, and they do what anti-parallel magnetic fields in plasma always do. They reconnect. The field lines break, rejoin in a new configuration, and the barrier between the solar wind and the magnetosphere effectively opens. Energy floods in. Particles get accelerated. Currents surge through the upper atmosphere. The magnetosphere itself gets reshaped, compressed on the sunward side, stretched into a long tail on the night side, and all of that restructuring releases enormous amounts of energy back into the near-Earth environment. The stronger the southward BZ and the longer it persists, the more energy enters, and the more intense the resulting geomagnetic storm becomes. Essentially, every major geomagnetic storm in the observational record has been driven by sustained strong southward BZ conditions, not by flare size, not by CME speed alone, by BZ. Here is where the problem gets genuinely frustrating. We cannot reliably predict what BZ will be at impact until we actually measure it at the Lagrange 1 point, which is a gravitational sweet spot about 1 million miles upstream of Earth, where we have spacecraft continuously monitoring the incoming solar wind. That gives us roughly 30 minutes to an hour of warning before the plasma reaches us, and that is it. That is the window between knowing the storm is coming and knowing how bad it will be. Why can we not predict it sooner? Because the magnetic structure inside a CME is extraordinarily complex and actively evolves during transit. When a CME leaves the Sun, its magnetic field configuration reflects the twisted, sheared geometry of the source region, a flux rope structure that looks a bit like a tightly coiled spring of magnetic field lines. As it moves through interplanetary space, that structure rotates, it expands, it interacts with the background solar wind, with other CMEs, with high-speed streams. It can twist, flip, compress, fragment. By the time it reaches Earth, its magnetic configuration may bear only passing resemblance to what it had when it left the Sun. We can sometimes make inferences from the magnetic configuration of the source region on the solar surface, looking at the sunspot structure, the polarity distribution, the orientation of the polarity inversion line. Solar physicists have developed techniques for estimating the likely BZ orientation of a CME based on these source characteristics, and when everything aligns nicely, those estimates can be reasonably accurate, but the error bars are wide. A CME that leaves the Sun with what looks like northward magnetic field dominance can rotate during transit, interact with other plasma structures, or evolve in ways that produce southward BZ at Earth. The reverse also happens. Forecasts predicting strong southward BZ can turn out to be mostly northward when the cloud actually arrives. The prediction skill on this specific parameter has improved over the decades, but it remains low compared to almost everything else in space weather forecasting. This is why storm intensity forecasts always carry significant uncertainty. We know the size of the event. We know the speed to within a reasonable margin. We know approximately when it will arrive, usually within a window of about 6 hours. What we do not know, until approximately 30 minutes to an hour before impact, is whether the event will produce a major storm or a minor one. The difference between a G1 storm and a G4 storm, between something barely noticeable and something with actual infrastructure consequences, can be decided by whether BZ happens to be pointing up or down when the plasma arrives. And that uncertainty is not a problem that better computer models will solve. It is not a problem that more data will close. It is due to genuine physical unpredictability of magnetic field evolution during transit through a turbulent structured medium we cannot observe in detail. For the current event, the BZ prediction is particularly uncertain, and the reasons compound in ways worth understanding. If the X2.5 flare's CME actually merges with the earlier M-class CME, as some ensemble model runs suggest, the magnetic structure that arrives at Earth will be a combined cloud, with properties that neither source event had individually. The merging process scrambles BZ. Field lines from one cloud reconnect with field lines from the other, the resulting structure can have multiple reversals of orientation packed into a single transit, and the BZ profile that sweeps past Lagrange 1 can flip direction several times over the course of the event. Each flip triggers or ends a round of energy coupling with Earth's magnetosphere, producing a storm that ramps up, subsides, and ramps up again in ways that sustained BZ events never do. The coronal hole high-speed stream adds another layer of complication. If that stream arrives roughly simultaneously with the CME, it will compress the trailing edge of the CME against the slower ambient solar wind, intensifying magnetic structures in that region and making BZ behavior even more variable. The multiple interacting factors do not just widen the uncertainty, they qualitatively change the kind of uncertainty we are dealing with, from a relatively predictable single event forecast to a genuinely hard-to-predict combined event forecast with multiple possible failure modes, each with its own probability and its own potential impact. Storm strength is determined at impact, not at launch. I want you to hold on to that sentence because it captures something profound about how space weather actually works. The flare size, the shock speed, the radio burst intensities, all the parameters that get headlines when a major event occurs tell us something about the event that launched. They are useful. They are not noise, but they do not determine the geomagnetic response. That response will be determined by what BZ does when the plasma actually arrives at Earth, and BZ is a hidden variable we cannot read in advance. We can only watch it reveal itself in the last 30 minutes before impact. This is why even so-called minor storms matter in the current environment, because they are not happening in isolation. They are happening in the context of a highly active sun, a multi-region configuration producing coherent activity across the disk, and a cycle that has been defying decline forecasts for more than a year now. Their effects can compound in ways that a single event wouldn't. A G1 storm, followed by another G1 storm, followed by a surprise G3, when BZ turns out to be sharply southward on the third event, produces cumulative stress that no individual storm would. The central thread of this entire analysis leads directly here. The sun has fired once. More events are likely, and the one parameter that will determine how bad any of them get is the one parameter we cannot see coming until it is effectively already here. Part 14. Satellites are the weakest link. Low Earth orbit is currently more crowded than at any point in human history, and that statement is not hyperbole. It is a straightforward description of a situation that has changed more in the past 5 years than in the previous 5 decades combined. Approximately 11,000 active satellites occupy altitudes between about 160 and 2,000 kilometers above Earth's surface, with the majority concentrated in the Starlink constellation and a growing number of similar commercial broadband networks operated by Amazon, OneWeb, Chinese state providers, and a half-dozen other aspiring mega-constellation operators. To put that number in context, as recently as 2019, the total number of active satellites in all orbits combined was under 2,000. We have added more than 5 times that number to low Earth orbit alone in under 7 years, and the deployment rate is still accelerating. This density is unprecedented, and it has changed the nature of how space weather events translate into actual infrastructure risk. The old calculus, where space weather affected a relatively small number of expensive, well-shielded, professionally operated spacecraft, has been replaced by a new calculus, where space weather affects vast commercial constellations of relatively simple satellites with thin margins for error. The same storm that would have caused operational inconvenience for a dozen geostationary satellites in 2010 can now affect thousands of low-altitude satellites simultaneously, and the economics of that exposure are dramatically different. To understand why, you need to understand what actually happens to satellites during a geomagnetic storm. The upper atmosphere, specifically the thermosphere at altitudes between roughly 80 and 600 kilometers, heats up dramatically when the magnetosphere absorbs energy from the solar wind. That heating causes the atmosphere to expand outward, which means that at any given altitude, the atmospheric density increases substantially. During a major storm, density at 400 kilometers altitude can increase by a factor of 2 or 3, sometimes more, and any satellite moving through that denser atmosphere experiences proportionally more drag. Drag, in orbital mechanics, is the enemy of sustained operation. Every satellite in low Earth orbit is slowly losing altitude all the time, constantly being pulled back toward Earth by the thin but non-negligible atmospheric resistance at its operating altitude. Operators compensate for this through periodic propulsion burns, small maneuvers that boost the satellite back to its intended altitude. The propellant budget for those maneuvers determines the satellite's operational lifetime. When drag spikes during storms, satellites either consume more propellant to maintain their orbits, or, in extreme cases, they lose altitude faster than their propulsion systems can compensate, and they re-enter the atmosphere prematurely. This is not a hypothetical risk. This is something that has already happened, at scale, within recent memory, to one of the most sophisticated space operations companies in the world. In February of 2022, a relatively modest geomagnetic storm caused SpaceX to lose approximately 40 Starlink satellites shortly after launch. The event was classified as a G1 to G2 storm, exactly the kind of event NOAA is currently forecasting for this weekend. Not extreme, not historic, just a moderately active period during a cycle that, at the time, most people were not paying particular attention to. The satellites had been deployed into a low insertion orbit, which is SpaceX's standard practice. The idea is that placing newly deployed satellites at a lower initial altitude allows controlled deorbit of any units that fail their initial health checks, preventing defective hardware from contributing to long-term space debris. It is a responsible engineering choice. Under normal space weather conditions, it works well. But on that particular day in February of 2022, the storm-enhanced atmospheric drag was sufficient to prevent the majority of the newly deployed batch from reaching their operational altitude before losing too much energy to recover. They burned up in the atmosphere within days of their launch. That loss represented tens of millions of dollars in direct hardware cost, plus the associated launch costs, plus the opportunity cost of replacing satellites that were supposed to be adding to the constellation. SpaceX weathered the loss without significant operational impact because they have an enormous manufacturing pipeline and can replace inventory faster than any space company in history. But the incident was a wake-up call for the industry. It demonstrated in unambiguous financial terms that even modest space weather events can produce catastrophic losses under the right conditions, and it forced every constellation operator to reconsider their space weather risk models. The current geomagnetic storm, even at its baseline forecast levels, will not produce losses comparable to the February 2022 event. And I want to be clear about that because I do not want to alarm anyone unnecessarily. There are no fresh satellite deployments currently exposed in the most vulnerable altitude range during this weekend's expected storm window. The specific confluence of circumstances that made February of 2022 so expensive is not present right now. Operational satellites at their proper altitudes have much larger margins for handling moderate drag increases, and the constellation operators have gotten better at scheduling launches around predicted storm periods. But the principle holds, and the principle is what matters for understanding the broader risk landscape. Geomagnetic storms produce drag. Drag produces orbital decay. Orbital decay shortens satellite lifespans and consumes propellant that would otherwise be available for operational maneuvers, including collision avoidance maneuvers that are becoming increasingly necessary as orbital populations grow. Every storm that passes through the near-Earth environment costs something, even if those costs are not always visible in headline terms. For the current constellation operators, the costs of moderate storms manifest in ways that do not make news. A Starlink satellite that would have operated for 5 years now operates for 4 years and 8 months, because storm-induced drag consumed propellant faster than expected. Multiply that across thousands of satellites, across multiple operators, across decades of unexpectedly active solar conditions, and you get a cumulative cost that is genuinely substantial, but distributed in ways that make it hard to trace back to any individual space weather event. Insurance premiums for satellites in low Earth orbit have risen accordingly. Launch schedules now factor in space weather forecasts in ways they did not 5 years ago. The economics of operating in low Earth orbit have been quietly reshaped by a sun that is producing more activity than anyone predicted. There is also a second-order effect worth mentioning, which is that increased drag variability makes orbital position predictions less accurate, and less accurate position predictions make collision avoidance more difficult. Every satellite's position is calculated based on models that assume certain atmospheric conditions, and when those conditions change unexpectedly during storms, the predicted positions diverge from actual positions. During quiet conditions, position predictions can be accurate to within meters over days, During storm conditions, those same predictions can accumulate uncertainties of kilometers over the same time period. Collision avoidance depends on knowing where everything is, and when everything's position is fuzzy, the collision risk rises, even if no individual satellite is in immediate danger. Even minor events from this active solar configuration can have real-world consequences when they affect infrastructure that now includes tens of thousands of satellites, spacecraft, and related systems. This is the connection back to the central thread of everything we've been discussing. The Sun's dual X-flare this morning demonstrated what the current solar environment is capable of producing in terms of raw energy output. The 3 loaded delta regions on the solar disk suggest additional events are likely over the coming weeks, and the infrastructure that has to absorb those consequences has never been more exposed to them, because we have never had this many things in low Earth orbit before, and those things have never been this dependent on consistent atmospheric conditions for their operation. The satellites are the weakest link in our space-based infrastructure, not because they are poorly engineered. They are actually, by and large, beautifully engineered. They are the weakest link because there are so many of them now, operating so close to the limit of what atmospheric conditions will allow, that any significant perturbation of those conditions creates measurable operational stress across the entire constellation ecosystem. A single major storm from the current solar configuration, if BZ cooperates in the wrong way and drag spikes to elevated levels, could produce satellite losses that the February 2022 incident would look modest by comparison. The current weekend event will not be that storm, but the conditions that produce such storms are present on the solar disk right now, and the next few weeks will tell us whether one of them actually develops. Part 15. The crash clock problem. Beyond individual satellite drag, there is a broader concern that has been discussed in space situational awareness circles for years and has grown genuinely pressing as orbital populations have exploded. The collision risk in low Earth orbit increases during geomagnetic storms, and the cascading consequences of major collisions could produce effects that persist not for years, not for decades, but potentially for generations. This is the kind of risk that sounds abstract until you actually sit with the math, and when you do sit with the math, it stops being abstract very quickly. Each satellite in low Earth orbit is tracked by space surveillance networks, primarily the United States Space Force's network of radars and optical telescopes, supplemented by commercial tracking operations and contributions from allied nations. These networks calculate close approaches, often called conjunctions in the technical literature, and predict potential collisions with lead times that can range from days in advance for well-characterized objects down to minutes for fast-moving or recently launched hardware. The entire system is a vast, continuously running exercise in celestial choreography, trying to keep tens of thousands of objects from hitting each other in a volume of space where even small velocity differences translate to catastrophic energy releases on impact. During normal conditions, this system works reasonably well. Operators receive conjunction warnings when the predicted minimum distance between 2 objects drops below established thresholds, and they respond by executing small orbital adjustments that move their satellites safely out of the conjunction window. These maneuvers are routine. Starlink alone conducts thousands of collision avoidance maneuvers every year, quietly, without public attention, because the system is designed to handle this kind of operational overhead. Most of these maneuvers are precautionary, based on probability estimates rather than certain collision trajectories, but the cumulative effort involved is substantial. During storm conditions, however, several things change at once, and the changes compound in ways that degrade the entire collision avoidance system simultaneously. First, many satellites enter safe mode during geomagnetic storms, deliberately deactivating attitude control systems and non-essential electronics to protect them from charging events and surface arcing that can occur when energetic electrons penetrate spacecraft surfaces. A satellite in safe mode is, by design, unable to execute maneuvers. It is prioritizing survival over operational capability. If a conjunction warning arrives during that safe mode period, the operator cannot respond to it in the normal way. Second, ground station communications may themselves be degraded by ionospheric effects during storms. The same ionospheric disturbances that cause radio blackouts for high-frequency communications also affect the uplink and downlink channels that satellite operators use to monitor their spacecraft and issue commands. Even for satellites that are not in safe mode, the ability to confirm their status and send maneuver instructions can be compromised at exactly the moment when those capabilities matter most. Commands that normally transmit in seconds may take minutes. Telemetry that normally arrives reliably may drop packets or require retransmission. The whole command loop slows down. Third, and perhaps most insidiously, the orbital positions of all satellites become less predictable during storms because of storm-induced drag variations. The models that predict where each satellite will be at any given future time assume certain atmospheric conditions, and when the thermosphere heats and expands unpredictably during storms, actual positions drift from predicted positions. Uncertainty ellipsoids, the three-dimensional regions within which a satellite is estimated to be at any given time, grow dramatically during storms. A conjunction that looked like a comfortable miss based on pre-storm predictions may suddenly look much tighter when the uncertainty grows, or vice versa. The whole collision risk picture becomes fuzzier exactly when sharpness is needed most. Put those three factors together, and you have a situation where the short reaction windows involved in collision avoidance during storm conditions represent a real operational challenge. Satellite operators under normal conditions have minutes to hours to respond to a conjunction warning, depending on the specifics of the geometry and the lead time provided by the tracking network. During storm conditions, that window can shrink further, either because the storm delayed detection of the conjunction in the first place, or because the operator's own ability to confirm and respond has been degraded by the storm's effects on their systems. Decisions that should be made with full information get made with partial information, under time pressure, with higher stakes. That is exactly the kind of situation where things go wrong. And when things go wrong in low Earth orbit, they go wrong in ways that last. A single collision between two intact satellites produces thousands of debris fragments, each of which becomes a new collision risk for every other satellite in the same orbital shell. The February 2009 collision between an active Iridium satellite and a defunct Russian Cosmos satellite produced over 2,000 trackable fragments and an unknown number of smaller untrackable pieces, many of which remain in orbit today, 16 years later. The 2007 Chinese anti-satellite test that deliberately destroyed a weather satellite produced more than 3,000 tracked fragments, several hundred of which are still in orbit and will be for decades to come. Every collision multiplies the hazard environment for every subsequent mission. The nightmare scenario, discussed seriously in space policy circles for more than 40 years, is called Kessler syndrome, named after the NASA scientist Donald Kessler, who first formally described it in 1978. The scenario works like this. Enough collisions occur in a given orbital altitude band that the debris population reaches a critical density. At that density, the rate at which debris fragments collide with other debris fragments, producing more debris fragments, exceeds the rate at which debris naturally deorbits due to atmospheric drag. The population becomes self-sustaining. More collisions produce more debris, which causes more collisions, which produces still more debris, in a cascading chain reaction that continues until the orbital band is so saturated with fast-moving fragments that operating functional spacecraft there becomes impossible. Kessler syndrome does not happen instantly. It unfolds over years or decades. But once it starts, it is extraordinarily difficult to stop because removing debris from orbit is technically challenging and economically unattractive, while preventing new debris requires global coordination that has historically been difficult to achieve. A Kessler cascade in low Earth orbit would render entire orbital altitudes unusable for generations, potentially setting back human space activities by half a century or more. Now, to be clear, none of this is directly caused by the current event. The weekend storm is not going to trigger Kessler syndrome. A single G1 or G2 storm is not going to produce the kind of mass conjunction failure that starts a cascade. What I'm describing is not the acute risk of this specific weekend. It is the chronic risk of operating in a crowded orbital environment during a period of unexpectedly elevated solar activity, and that chronic risk is what deserves attention. The cumulative stress of repeated geomagnetic storms from an unexpectedly active sun contributes to the broader risk profile in ways that compound over time. Every storm that degrades satellite control for a few hours is a storm during which collision avoidance capabilities are reduced. Every storm that increases uncertainty in orbital position predictions is a storm during which conjunction assessments get fuzzier. The probability of any given storm producing a catastrophic conjunction is low, genuinely low, not hypothetically low. but probability compounds. The probability of at least one such conjunction occurring over enough storms, across enough satellites, across enough years of unexpectedly active solar conditions becomes considerably more meaningful. This is the statistical trap that keeps space situational awareness professionals awake at night. It is not the catastrophic single event that they fear. It is the cumulative build-up of small probability risks, each individually negligible, combining across thousands of opportunities to produce an outcome that any rational risk assessment would have flagged as unacceptable if it were presented as a single decision. The low probability, high consequence event is always more likely than naive intuition suggests when the number of attempts is large enough. Repeated solar activity events, like the ones we are currently seeing from the 3-region configuration on the solar disk, increase the cumulative probability of serious infrastructure consequences, even if no single event is itself catastrophic. Every storm is another roll of the dice. Every period of degraded collision avoidance is another window during which something could go wrong. Every uncertainty spike in orbital predictions is another opportunity for a missed conjunction warning. The connection back to the central thread is that this unstable solar configuration does not just produce one event. It produces repeated events over weeks and months, and repeated events accumulate risk in ways that forecasters, operators, and policymakers are still learning how to properly model. The dual X-flare demonstrated what this configuration can do. The real question is how many more demonstrations we'll receive before the current active period ends. Part 16. Human exposure beyond Earth. Human spaceflight has its own vulnerabilities to space weather that deserve a brief mention in this discussion. The International Space Station orbits at approximately 400 kilometers altitude, well within Earth's magnetosphere, which provides substantial protection from solar energetic particles. The station's crew experiences increased radiation during geomagnetic storms, but generally at levels that remain within operational limits, and they can take shelter in more shielded areas of the station during the most intense events. The situation becomes more serious for missions beyond low Earth orbit, and that category of mission is expanding. Artemis missions planning lunar operations will spend time outside the protection of Earth's magnetosphere, where solar energetic particle events can pose genuine radiation hazards. Future human missions to Mars would face similar exposure over much longer duration, making solar activity prediction a mission-critical capability rather than a nice-to-have operational detail. The current solar activity, with its rapid development of major flares from multiple regions, illustrates why predicting the space radiation environment for crewed missions is genuinely hard. If Artemis astronauts were on the lunar surface during an event like the dual X-flare this morning, they would need to take shelter quickly, and the timing of that shelter response depends on having accurate early warning. The same uncertainty that makes ground-based space weather forecasting difficult makes crewed mission radiation planning difficult. Continued solar instability increases long-term exposure risks for missions that are now being planned and executed in the shadow of a solar cycle that refuses to decline on schedule. The central thread here is that every major event from the current configuration contributes evidence to the case that solar cycle 25 is not behaving as predicted, and that contradiction has implications far beyond any single weekend's geomagnetic storm. Part 17. Power grids and the illusion of resilience. Modern power grids are generally robust against minor geomagnetic storms. G1 events typically produce effects that grid operators can manage through routine operational adjustments. G2 events introduce more voltage fluctuations and may require some active mitigation, but still fall well within standard operational capacity. The infrastructure is engineered with space weather effects in mind, especially for grids at high latitudes where geomagnetically induced currents are most likely to develop. The concern is not individual events, it's repeated events combined with the cumulative stress they place on aging infrastructure. Transformers that experience geomagnetic currents don't typically fail immediately. They accumulate damage over many storm events, with each exposure producing small amounts of thermal stress and insulation degradation. Eventually, a transformer that has absorbed decades of minor space weather stress can fail during an event that, on its own, would not have damaged a fresh unit. Additionally, the assumptions built into grid resilience models generally date from earlier periods of solar cycle behavior. If the current cycle is producing more frequent moderate events than historical baselines suggested, The cumulative stress accumulation is happening faster than the infrastructure lifecycle models anticipated. That's not a crisis. It's a slowly evolving vulnerability that becomes more visible with every unexpected active period. Repeated events from the current solar configuration matter more than any single storm. The central thread continues here. The dual X-flare wasn't just a one-off. It's part of a pattern of elevated activity that adds to cumulative exposure across infrastructure systems that have their own aging timelines, their own assumption bases, their own limits. Part 18. Solar Cycle. 25 broke the script. Here's where the story gets genuinely strange, and where we have to step back from immediate events to look at a pattern that nobody expected to be looking at right now. Solar Cycle 25 began in December of 2019. At that time, NOAA's Solar Cycle Prediction Panel, drawing on the best available solar dynamo models and the collective expertise of the solar physics community, issued an official forecast. That forecast predicted a weak cycle, similar in amplitude to Solar Cycle 24, which itself had been one of the weakest cycles in over a century. The predicted maximum monthly smooth sunspot number was approximately 115, and it was expected to occur around July of 2025. The cycle was then expected to decline gradually through 2026 and into 2027, approaching solar minimum sometime in 2030. That forecast did not survive contact with reality. By 2023, solar activity had already exceeded the predicted levels. Sunspot numbers were running substantially higher than the forecast. Major flare productivity was exceeding expectations. The cycle was clearly going to be stronger than NOAA had projected. In late 2023, NOAA revised the forecast upward, now predicting peak activity between January and October of 2024, with a higher sunspot number than originally expected. Even that revision proved conservative. The observed peak occurred in late 2024, and actual peak sunspot numbers exceeded even the revised forecast. Major flare productivity remained elevated throughout 2025, and now, in late April of 2026, well into what should be the declining phase of the cycle, we're seeing not just continued activity, but apparently intensifying activity, with the most volatile magnetic configuration of the entire cycle appearing this late in the game. That contradiction demands an explanation. Solar cycles are supposed to follow a relatively predictable shape, rising toward maximum over roughly 4 to 5 years and declining back toward minimum over the following 6 to 7 years. The decline phase is supposed to feature decreasing overall activity, with the largest events typically occurring during the rise and peak phases. A cycle that produces its most dangerous magnetic configurations during the declining phase is not behaving according to the standard model. One interpretation is that the cycle has not actually peaked yet, and that what we called the peak in late 2024 was actually just the first of multiple peaks. That's a known phenomenon in solar cycle history, where some cycles exhibit double-peaked or multiply-peaked maxima. If the cycle has a second peak still coming, the elevated activity we're now seeing might be the beginning of that second peak, rather than an anomaly in the decline. Another interpretation is that solar cycle prediction models are simply less accurate than we thought, and that the apparent prediction failure reflects fundamental limits in our ability to forecast the sun's behavior beyond approximately one cycle in advance. That's a humbling possibility, and it's one that some solar physicists have been arguing for years. Either way, the observed 2026 activity contradicts the decline narrative that dominated forecasting through much of 2025. Something is happening on the sun that our models did not capture. And the current multi-region configuration, with 3 simultaneously active delta regions, is evidence of that something, whatever it is. The cycle may not have peaked. That possibility changes how we should think about the current risk window. Part 19. The false decline hypothesis. In solar cycle terminology, a secondary peak refers to a second maximum of activity occurring after an initial maximum has been identified, typically separated by a period of reduced but not minimum activity. Not every cycle has a secondary peak, but enough cycles have exhibited this behavior over the observational record that it's a recognized phenomenon rather than a one-off anomaly. The hypothesis worth considering for Solar Cycle 25 is that what we observed as the peak in late 2024 may have been only the first peak, and that current activity levels represent either a continuation of elevated activity or the beginning of a secondary peak that will become more pronounced over the coming months. If that hypothesis is correct, we are not in the declining phase at all. We're in an extended activity phase, and the events we're now observing are consistent with that phase rather than being anomalies in a proper decline. There's a specific historical precedent that's worth mentioning because it illustrates what late-cycle extreme activity can look like. The Halloween solar storms of late October and early November of 2003 occurred during the declining phase of solar cycle 23. That cycle had peaked in early 2001, and by late 2003 was well past peak. Yet that period produced some of the largest solar events of the entire cycle, including an X-28 flare, one of the largest ever recorded, and multiple other X-class events that drove extreme geomagnetic storms and caused actual infrastructure impacts on Earth, including power outages in parts of northern Europe. The lesson from the Halloween solar storms is that the largest and most dangerous events of a given solar cycle do not necessarily occur at the cycle's peak. They can occur during the declining phase. The physics that drives major events, the buildup of complex magnetic structures in active regions, does not care about our classification of cycle phases. It operates on its own timescales, and those timescales can produce outliers well outside the expected distribution. If solar cycle 25 is following a pattern similar to the one observed in cycle 23, then the current phase might be more active than the standard decline narrative suggests, and the dangerous events of this cycle may still be ahead of us rather than behind us. The dual X flare from region 4419 and the simultaneous presence of 3 delta regions is consistent with that interpretation. It's exactly the kind of activity that late-cycle extreme events tend to produce. Why would this happen? What's the physical mechanism that could cause a solar cycle to produce its most dangerous events during a phase when overall activity is supposed to be declining? That question doesn't have a definitive answer, but there are several hypotheses worth considering. Part 20. Magnetic memory in the solar dynamo. The Sun's magnetic field is generated by what's called the solar dynamo, a complex fluid dynamical process occurring in the deep convection zone where hot ionized gas undergoes differential rotation and turbulent motions. The dynamo converts kinetic energy of solar rotation and convection into magnetic energy, which then emerges to the surface as active regions and sunspots over the course of an 11-year cycle. One feature of the solar dynamo that's been studied but remains incompletely understood is the concept of magnetic memory. The magnetic field at any given time in the cycle depends not only on the current state of the dynamo but also on the history of what the dynamo has produced over previous cycles. Residual magnetic flux from prior cycles can persist in deeper layers of the convection zone, emerging later in unexpected ways. The dynamo has, in a sense, a memory of what it has done before, and that memory can influence current behavior in ways that simple single-cycle models don't capture. If solar cycle 25 is being influenced by residual flux from cycle 24, or from deeper cycles before it, the current elevated activity might reflect delayed energy release from storage structures that aren't directly visible in standard cycle observations. The current multi-region instability, with 3 simultaneous delta regions, could be partially fed by that stored energy, producing a more complex magnetic surface configuration than the primary dynamo cycle alone would generate. This is speculative. Dynamo modelling remains an area of active research, and different modelling approaches produce different predictions about how magnetic memory should affect observable cycle behaviour. But the general concept that the Sun's current activity may not be fully explainable by the current cycle's dynamo state alone is one possible framework for understanding why we're seeing these unexpected configurations. Stored magnetic energy, released late in the cycle, may explain the multi-region instability we're currently observing. The central thread of our argument is supported by this possibility. The current configuration isn't a one-off coincidence. It's potentially a signature of deeper processes that have been building for longer than a single cycle and are only now becoming visible at the surface. Part 21. Multi-region coupling hypothesis. Another idea worth exploring, and one that's been receiving increased attention in recent solar physics research, is that active regions on the Sun are not as independent as classical models treat them. The solar surface and near-surface layers can host large-scale magnetic connections between regions that are apparently separated by significant distances, and those connections can allow events in one region to influence conditions in another. The observational evidence for this comes from phenomena like sympathetic flaring, where multiple active regions flare in close temporal succession despite being too far apart for any simple causal mechanism. Some of these sympathetic events have been traced to large-scale magnetic loops connecting the regions, with disturbances propagating through those loops at alphinic speeds, fast enough to trigger destabilization in connected regions within minutes of the initial event. If the 3 delta regions currently on the Sun are magnetically connected in this way, the implications are concerning. A major flare in one region could potentially trigger or contribute to destabilization in the others. The timing of such coupled events would be unpredictable in detail, but the probability of a rapid succession of major events across multiple regions would be elevated compared to a scenario where each region evolves independently. Research into multi-region coupling is still in relatively early stages, and there's no consensus yet on how common or how significant these interactions actually are. But the current solar configuration provides a potentially informative test case. If we see major events from multiple regions in close temporal succession over the coming weeks, that observation would support the coupling hypothesis. If events stay relatively isolated in time, the hypothesis would be less supported. The solar surface may behave more like a connected system than a collection of independent active regions. The central thread of this analysis suggests exactly that. The current Sun is displaying coherent distributed activity across multiple regions in ways that don't reduce easily to a simple single-region explanation. That connectivity, if real, is part of what makes the current configuration genuinely dangerous. Part 22. The question that actually matters. Let me reframe where we are now, because I want to pull everything together into the question that actually matters for the coming weeks. The events of today, the dual X-class flare from region 4419, the Earth-directed CME component, the approaching geomagnetic storm, all of those are real, and all of those will have their consequences playing out over the coming days. But as significant as those events are, they're not the most important thing to watch for. They're the warning signal, as I've said throughout this analysis. The question that actually matters is this: what happens when one of the other delta regions, particularly region 4420, reaches the same critical instability threshold that region 4419 reached, and does so while positioned at central meridian with maximum Earth-directed geometry? A major X-class flare from region 4420, occurring during its transit through the geoeffective zone, would produce a CME aimed almost directly at Earth. If that CME is shock-driven, as today's event was, it could reach Earth within 24 to 36 hours of the flare. And if it arrives in a solar wind environment already disturbed by ongoing activity from the current multi-region configuration, the interaction effects we've discussed could compound in ways that produce a geomagnetic response significantly above baseline expectations. The conditions for escalation exist. I'm not predicting that they'll be realized. I'm not saying that next week will bring a catastrophic geomagnetic event. What I'm saying is that the underlying conditions, the solar configuration, the multiple delta regions, the evidence from today's event of what this configuration can produce, all support the assessment that the risk window is elevated and that a major Earth-directed event is within the realm of realistic possibility during the coming weeks. That's not alarmism. That's just pattern recognition applied to the observational evidence. The Sun is in a state it wasn't supposed to be in at this point in the cycle. It has demonstrated capacity for rapid-fire X-class events. It has multiple regions capable of repeating that demonstration, and at least one of those regions is rotating into a position where any repeat performance would aim its consequences directly at us. We're not in a period of solar quiet. We're in a period of continued activity that the official forecast didn't anticipate, and the scientific community is still working to understand. And during that period, we should be watching the solar disk more carefully than we might have been watching it 6 months ago, because the conditions for escalation are present in a way they rarely are. Part 23. What we know. Let me summarize what we actually know at this point, so the boundary between fact and uncertainty is clear. We know that region 4419 produced 2 X-class flares within 7 hours on April the 24th of 2026, an unusual cluster of high-energy events from a single source region. We know that the second of those flares launched a coronal mass ejection, with a shock front moving at approximately 1,293 km per second, and that NOAA modelling has identified a partial Earth-directed component. We know that the CME is expected to arrive in the late hours of April 25th through April 26th, with a baseline forecast of G1 minor storm conditions and possible G2 moderate storm levels if interaction effects amplify the response. We know that there are currently 3 Delta-class magnetic regions on the Earth-facing solar disk. We know that region 4420 is rotating towards central meridian and is the largest of the 3, with complexity that has been increasing over the past several days. We know that region 4423 is a newly emerging region with rapid development and existing delta structure. We know that the multi-region configuration is unusual, producing coherent activity across distributed locations rather than the isolated events we'd expect during a quieter phase. We know that solar cycle 25 has been producing activity above the originally predicted levels since 2023, and that current activity in late April of 2026 contradicts the declining phase narrative that dominated forecasts through much of 2025. We know that secondary peaks have been observed in other cycles, and that the Halloween solar storms of 2003 demonstrated that late-cycle extreme activity is a recognised phenomenon. We know that the infrastructure exposed to space weather effects has never been more extensive. More satellites in low Earth orbit than ever before. Power grids that depend on long-distance transmission in ways that make them vulnerable to geomagnetically induced currents. Communication and navigation systems that rely on ionospheric conditions that geomagnetic storms can disrupt. Space-based assets that support everything from global navigation to weather forecasting to financial transactions. We know all of that. The evidence is clear, the data is available, and the implications are reasonably understood by the relevant expert communities. The central thread holds. The sun fired. The CME is coming. The conditions for more events are present. This is the factual ground we're standing on. Part 24. What we don't know. Against that factual ground, we need to honestly acknowledge everything we don't know, because the scale of the uncertainty is substantial, and it shapes how we should think about the risk. We don't know whether the X2.5 flare's CME will actually merge with the earlier M-class CME in transit. We don't know what BZ orientation either CME, individually or merged, will have when it arrives at Earth. We don't know whether the high-speed stream from the coronal hole will amplify or extend the resulting geomagnetic disturbance, or whether it will arrive separately without meaningful interaction. We don't know whether region 4420 will produce an X-class flare during its transit through the geo-effective zone, or whether it will pass through that zone with only M-class activity or less. We don't know how long region 4423 will continue developing, what peak magnetic complexity it will reach, or whether it will become a major flare producer or settle into a more modest activity level. We don't know whether the current elevated solar activity represents a true secondary peak in cycle 25, or just an extended period of elevated activity within a broader decline. We don't know how much of the current multi-region configuration reflects underlying dynamo processes versus short-term coincidence of multiple regions emerging in similar timeframes. We don't know whether the sun will continue producing events at this rate for days, weeks, or months. We don't know in general how any given future event will behave until it actually occurs. Space weather forecasting has improved substantially over the past few decades, but it remains fundamentally limited by the physics of the systems involved and by the observational coverage we have available. The unknowns in space weather are not gaps that better instruments will close in the next year or two. They are, in some cases, fundamental uncertainties in how the sun and the solar wind behave. What we don't know shapes the risk profile as much as what we do know. The range of possible outcomes over the coming weeks is wide, and the decisions about how to respond to that range depend on how we weight different possibilities. A world where region 4420 stabilizes without major flaring looks very different from a world where it produces a central meridian X-class event. Our models can't tell us which world we're in yet. Part 25. The real ending. Let me close with the framing I want you to carry away from this analysis. The event that happened today, the dual X-class flare from region 4419, has already happened. Its consequences are already in motion. The CME is in transit. The geomagnetic response is coming this weekend. None of that can be changed, and none of it will, in isolation, represent a major crisis. The baseline forecast of G1 to G2 storm conditions, possibly extending higher with interaction effects, is an event our infrastructure is generally equipped to handle. The real story is not the event that already happened. The real story is the risk window we're now in. The current solar configuration, with its 3 simultaneously active delta regions and its demonstrated capacity for rapid-fire major flare production, represents conditions that make additional major events plausible over the coming days and weeks. Some of those events, if they occur, would be launched from regions with direct Earth-facing geometry, producing impacts significantly more severe than what this weekend will bring. That's not a prediction, it's a characterization of the risk environment. The Sun has given us a demonstration. What we do with that information, how closely we watch for additional signs of instability, how seriously we take the possibility that solar cycle 25 hasn't actually peaked, determines whether the demonstration serves as a useful warning or as a forgotten anomaly before the next more significant event catches us unprepared. The configuration that produced today's event is still present. The Sun's rotation is bringing the most dangerous region into the most dangerous alignment over the next few weeks. The possibility of CME interactions and amplifications is real. The track record of solar cycle 25 exceeding expectations is well established, and the infrastructure that would have to absorb the consequences of a larger event is more exposed than it has ever been. This isn't a story that ends this weekend. This is a story that's still being written, with the next several weeks representing the period during which we'll either get additional events from the current configuration or watch it gradually stabilize as the active regions rotate off the Earth-facing disk. The outcome is genuinely uncertain. The stakes are real, and the evidence in front of us, the evidence the Sun itself provided this morning, tells us that the conditions for something larger are present. So here's what I'd leave you with. The Sun has already fired once. What we witnessed this morning was a warning shot, not the main event. The magnetic chambers are still loaded, the rotation clock is still running, and the central meridian is still filling with active regions capable of producing events far more directly aimed at us than today's event was. The only question now is whether the next shot comes when the barrel is pointed directly at us. Keep watching the Sun, because the Sun is definitely watching us.